Watch it. We have already seen this model, but then I still want to examine it one more time. See, we have 4 processes P0, P1, P2, P3, and we have 4 mutexes 0, 1, 2, 3. And now each process is performing down like this, and then critical section, and then up like this. So Pi is performing down on Mi, and then Mi plus 1 mod 4. So the same kind of code. Earlier we have seen it, right? So if you write down what are all the process and what is happening here, you can see that P0 wants to perform down on one is M0 and other is M1, and similarly P1 wants down on one is M1 and other is M2, and P2 wants to perform down on one is M2 and other is M3, and P3 wants to perform down on one is M3 and other is M0, right? So obviously the problems are there. So one problem is that if that is a critical section, one problem is that more than one process can be in the critical section simultaneously. What are the two processes here? P0 and P2 can be in the critical section simultaneously because they are actually waiting on different semaphores completely. So P0 wants 0, 1 and P2 wants this one, right, 2 and 3, and even P2 and P1 and P3 can also be in the critical section at the same time. Okay, fine, that is okay. And what about the deadlock? Deadlock is also possible, isn't it? And see, assume that critical section is such a way that it is such a kind of critical section where two processes can be present inside the critical section, then it is fine, the solution is going to work, right? So I'm not looking at the mutual exclusion now. Even if more than one process gets into the critical section, I'm not worried about it. I am allowing two processes to get into that, and this code is allowing two processes, either P0 and P2 or P3 and P4. That is fine. But then the main issue is deadlock. I don't want deadlock to happen here. See, here deadlock is possible, isn't it? How is deadlock possible here? If every process gets preempted after the first down, then P0 will take M0, P1 will take M1, P2 will take this, and P3 will take this. Therefore, after this, everything is going to fall in deadlock, right? So deadlock is going to be possible if every preemption is like this. Definitely deadlock is possible, right? Now, if you want to change the deadlock, if you don't want deadlock to happen here, maybe you could do one thing and try here. For P0 to P3, you run this code, and for the P4, only for P0 to P3 you run this code, and for P4 you run a different code. Instead of waiting on P4 and then P0, why don't you wait for P0 and then P4? I am waiting on the same semaphores, sorry, P3, right? Here there is no 4. So I am talking about process 3, and instead of waiting on P3 and then P0, why don't you wait on P0 and then P3? Which means what happens if I wait here on M0 and then M3 instead of waiting on M3 and M0? Now watch it. Even though these three processes have finished their first line, which means P0 has taken this, P1 has taken this, P2 has taken this. Now P3 will not take P0 first. Whenever P3 tries to get P0, it will get blocked without holding P3, which means even if we say that P0 has taken M0 and got preempted, P1 has taken M1, right, and got preempted, and P2 has taken M2 and got preempted. Now P3, when it tries to take M0, obviously it will get blocked because M0 is already taken up, right? So now P3 got blocked, and now let us say P0 is again executing, right? Then it will try for M1 and it will get blocked because it is already taken by P1, therefore it is getting blocked, isn't it? P1 has already taken it, and then P1 will come into execution, and then it will take M2. See, why only this sequence is possible? Because this is a deadlock sequence earlier, that is why I am exploring it, okay? And now if I try to do down on M2, then M2 is already taken by P2, therefore P1 will also get blocked. And now finally, if P2 is scheduled, then what happens? P2 will try for M3, right? M3, and now will it get blocked? It will not get blocked because M3 is not held by P3. M3 is still free. So in this case it will not get blocked and it will successfully enter the critical section, and after entering the critical section it is going to release P2 is going to release, what is it? P3 is going to release 2, mutex 2 and then mutex 3. So 2 and 3 are now available, therefore this one will get unblocked, P1 will get unblocked, and then yes, P1 will get unblocked, and therefore it can enter the critical section. Once P1 gets unblocked, it can release 1 and 2, so therefore P0 will get unblocked. Therefore once P0 get unblocked, it will release 1 and what is it 1? Yeah, 0 and 1. So it will release 0 and 1. Therefore P3 can get unblocked. So just by changing the sequence of the last one, we are able to break the deadlock, right? So if you want to watch it another way, watch it this way. Now assume that there is P0, there is P1, there is P2, there is P3, right? 4 process. I am just putting them in a circle, and now there is M0 and M1, M3, M2 and M3, right? Now here the rules are like this. Let me rearrange them. M0, M1, and then let me put M2 here, and let me put M3 here, right? So see this, P0 wants M0 and M1, and then P1 wants actually M1 and M2. So okay, circular form is not working out here. How can I put it? I want to put it this way. Let's write like this: P0, P1, P2, P3. P0 wants 0 and 1, right? I mean mutex 0 and 1, and P1 wants mutex 1 and 2, 1 and 2, and P2 wants mutex 2 and 3, and P3 wants mutex 3 and 4, 3 and 0, isn't it? So now every process, if it is taking the let's say this is the right side or clockwise, right? So let's say the clockwise one first and then the anti-clockwise, clockwise one and then the anti-clockwise, right? And clockwise one and then anti-clockwise, clockwise one and then anti-clockwise. I think here it is 3. So if they are all following one direction of choosing the semaphores, then there is a problem, isn't it? So instead of that, if you change the direction at one process in such a way that it will follow out of order, I mean if everyone is taking the left side one first and then the right side, then there is a problem of deadlock, right? So in order to break it, just let one process choose it out of order, which means if everyone is taking the left side one first and then the right side, left side one and then right side, just make sure that at least one process will take right side one first and then left side. If you apply that, then the deadlock will be broken. And the same concept can be extended to a problem called as dining philosopher's problem. I'll tell you what dining philosopher's problem is. Watch it. So there will be, the problem is like this. You know a philosopher, right? Philosopher is a thinker. Oh, he will keep on thinking. Now dining philosopher means now the philosophers will do only two things. One is they will keep on eating food, that is spaghetti, and then they will keep on thinking. So now the 4 philosophers are sitting like this. Assume that it can be extended to even n. 4 philosophers are sitting like this, and now in order to eat spaghetti they need 2 forks, 2 spoons, right? And one spoon is here, other spoon is here, one spoon is here, other spoon is here. Therefore there are 4 spoons, and then 4 philosophers are dining. And in order to dine, for one philosopher to finish, he is supposed to take 2 forks, 2 spoons, and then have the meal, right? But the problem is, if everyone is going to take the left one first and then the right one, right? Which means if this fellow takes this one first and then this one, and this fellow takes this one first and then this one, and this fellow takes this one first and then this one, like that. If everyone is taking the left one first and then the right one, what happens is the same thing will happen. So if everyone takes 1, which means if this one takes this one, and if he takes this one, and if he takes this one, and if he takes this one, then what happens? Everyone will get 1 spoon each, right? And then they will all wait for the second spoon to finish the meal, but then the second spoon they will never get it, right? So the same problem can be extended to this problem, and in order to solve this problem, if everyone is taking the left one first and then the right one, just make one person to take the right one first and then the left one. If you can make it, then what happens is, this fellow, let us say this fellow is not supposed to take left one first, then he will just turn around and see the right one, and this is not available, therefore he will not take anything, right? Then this fellow will obviously take this spoon, and he will finish the meal, and these two will be available, right? And once these two are available, this fellow will take this and he will finish the meal, and these two are available. And once this fellow finishes, this fellow will take this one, and these two are, like that everything will be done. So whenever you have lots of process working in, waiting for the mutexes in one order, just make the last one to wait in the reverse order, or just make anyone to make, to wait in the reverse order. Using that we can break the deadlock. So based on this, there is one question asked. In dynamic philosopher's problem, the philosopher's problem is like this: everyone will take the left one first and then the right one. If that is the case, in order to break the deadlock, what should we do? Make one philosopher in order to take the right one first and then left one. So in case of this, it is like this: if everyone is waiting for 0, 1, 1, 2, 2, 3 in this ascending order, just make at least one of them wait in a reverse order, which means instead of waiting for 3 and 0, make them wait for 0 and 3. If you could do that, this problem can be solved. Understood this? Okay.